7.1, the title is The Integral as Net Change, and I have here a quick quiz for you also for 7.1. You are asked to find all the values of x at which the function changes sign on the given interval. We're going to go over some things that will be a review for you, but you know, that's always good anyway. So we have the situation where a honeybee makes several trips from the hive to a flower garden. Isn't he cute? Look at him waving at us. The velocity graph is shown below. So take a second just to interpret that and understand what that's saying. This is his velocity, so he's going 100 feet per minute over 0 to 2, and then he's at 0. And then he's going negative 100 feet per minute over 2 to 4, and then he's at 0. So you can see where he's stopping and starting and when he is going to the hive and from the hive. What is the total distance traveled by the bee? This looks like a pirate problem we had recently when I asked you to find total distance when you were given a graph. We know that total distance would be the total area of the curve to the x-axis, and that is taking into account both the positive and negative values here. So total distance would be making all of those values positive and then adding them together. So we can see that the bee traveled 700 feet total when we take into account his trips back and forth from the hive. But what if we asked to find the displacement of the bee, or where the bee actually was in relationship to the hive after that 10 seconds? So in the first 2 seconds he went 200 feet away, and then he's coming back 200 feet away, and then he's coming back 100 feet. So when we add together all of those values with their respective signs, we will see that he is 100 feet towards the hive. To find the displacement, or the position shift, from the velocity function, we just integrate the function, because the integral takes into account net change. The negative areas below the x-axis subtract from the total displacement. However, and then we see there that displacement is the integral from a to b of v of t dt. However, if I now ask you to find total distance traveled, we have to take into account those negative areas that were maybe below the x-axis and making them positive. So that's why we say distance traveled is the integral from a to b of the absolute value of v of t dt. So all of this is review. You find the roots, remember, of the velocity equation, and then you just integrate in pieces. So if you have the velocity function crosses at 3, you integrate from 0 to 3, and then from 3 to 5 or whatever. You make all those values positive, and then you add them together. You can also just put it on your calculator and integrate the absolute value of the velocity function. That is another way to do it if you are on a calculator active section of the AP test. Okay, so we have a velocity graph here. We're going to answer a few questions about this velocity graph. If I asked you to find the displacement, displacement is the net area, and so that first piece is an area of 1. Second piece is 1/2. The third piece is 1/2, but it's below the x-axis. And that last piece is an area of 2. So with displacement, you have to take into account their positive and negative values. So we have 1 plus 1/2 minus 1/2 minus 2. So our displacement is negative 1. But if we were asking you the distance traveled, all those values would become positive. And so we have 1 plus 1/2 plus 1/2 plus 2, which is 4. So even though we ended up negative 1 units away from where we started, we actually traveled a total of 4 units to get there. And then we have a position graph for that velocity graph. And you can see over the course of this position graph, its maximum is at 2. And that should make sense, because if area under the curve of the velocity is the position, the maximum area will occur at 2, because after 2 this area is now negative and taking away. Okay? And then at 4 is where it equals the other side, top and bottom. So that's where it's now switching to a negative area total. Okay? Nearly every AP exam has had at least one problem requiring students to interpret velocity and position graphs, and there actually are usually a lot more than just one problem requiring you to do that. So position, velocity, acceleration, all of those things are very important to understand. Okay, I'm kind of going to go through parts of this on the PowerPoint. I left it on the PowerPoint because just for you to have reference of it in the future. But in the linear motion equation, the rate, your rate, which is your velocity, we have velocity being a function of time. If I send my dt to the other side, for a very small change in time, v of t can be considered a constant. Okay? Therefore, our change in s will equal our velocity times that little change in t. We add up all those little changes to get then that total distance. This should be recognizable as the area of a rectangle. Your height times your base gives you the area of that piece. And then we add up all those pieces. There we are. So there's our first piece, our second piece, our third piece, so on and so forth, to get our total area under the curve. And we have seen, let's just go a little farther here, that as the number of subintervals becomes infinitely large, meaning as we've put more and more and more rectangles into this, the width of them become very, very small, and that's what the definition of integration is. It's the sum, as the number of rectangles go from 1 to infinity, of those areas of those rectangles. The same technique is used in many different real-life problems. Here's the basic rule to solve these problems. If you are given a rate and you are asked to accumulate, then you need to integrate. I came up with that all by myself. If you're given a rate and you're asked to accumulate something over time, then you need to integrate that rate function to come up with how much you have with your accumulation over a certain time. So here's an example of what we're talking about: national potato consumption. The rate of potato consumption for a particular country was C of t equals 2.2 plus 1.1 to the t. So they have given you C of t being a rate, where t is the number of years since 1970, and C is in millions of bushels per year. For a small change in time, the rate of consumption is constant. So if I multiply together all those tiny little rectangles, or if I add together all those tiny little rectangles, I should come up with the consumption over that period of time. So let's go through and do this example. The amount consumed during the short period of time is the area of each of those rectangles. We add up all these small amounts to get the total consumption. Or, basically, you're just integrating your rate function. So if you are asked to come up with the amount of potatoes that were eaten over that certain period, we're just going to integrate the rate function. So from the beginning of 1972 to the end of 1973, I would integrate this from 2 to 4, because I'm going from 1972 to the end of 1973, so we're just going to integrate it all the way to 4 of my rate function with respect to t. When I do that, we have our integration, our antiderivative would be 2.2t plus 1 over the natural log of 1.1 times 1.1 to the t. That is one of your integration formulas. You could also just put this on your calculator, and you would end up getting 7.006 million bushels. And so what we found is that by integrating our rate function, we have actually found out that we consumed 7.066 million bushels in that 2-year time period. Work is another example of when we can integrate. We know work to be force times distance. So calculating work is very easy if you have a force and distance constant. However, if our force function varies, we are able to use calculus to solve that problem. And, we don't always have the same amount of force over the whole entire time period to calculate our work. There might be, in some of the work we do, the force being different at different points in time. So if we have a force function, then we can integrate it and we can get our work. So here's an example, Hooke's law for springs. Force is proportional to the distance that it travels. So x, the distance that the spring is extended beyond its natural length. K is your spring constant. So if it takes 10 newtons to stretch a spring 2 meters beyond its natural length, then I can find K. 10 is equal to K times 2, therefore K has to be 5. So what we've just done is, by saying that force is 5 times x, we've just come up with a force function, f of x equals 5x. The question now is asked how much work is done stretching the spring to 4 meters beyond its natural length. So we know that work is force times distance, but our force formula is 5 times x. It's not just a constant. So if I want to come up with the amount of work, we're just going to integrate it. So I'm going to integrate 5x. So the integral of 5x dx is 5 halves x squared. And then I'm going to integrate that over the interval 0 to 4. So when I put 4 in and 0 in, I will get 40 Newton meters. And 1 Newton meter is equal to 1 joule. And so the amount of work it would take for us to stretch that 4 meters beyond that spring 4 meters beyond its natural length would be 40 joules. And that is it. So come in tomorrow with your quick quiz. We are going to do a little fun thing with our little rhyme. So I think that's about it. So I think I'll just see you tomorrow, everybody. Bye.